This video is about waves and how they relate to electromagnetic radiation. Electromagnetic radiation is all around us, and that is how energy travels through space. So you're surrounded by it right now. And the different kinds are lots of things that you've heard about, such as radio waves, microwaves. Then we have IR, which is infrared, which then next in this little skinny part, this is what we call visible light. This is the only part we can actually see in this whole spectrum. We can't see microwaves or X-rays or anything. So infrared, then comes the red color light, right? Then we've got orange, yellow, green, blue, indigo, violet. After violet comes ultraviolet. Then we've got X-rays, and then this symbol right here is the Greek letter gamma. So these are gamma rays. So gamma rays are the highest energy. You can see the arrow right here, right? The energy increases as you get towards gamma rays, so they actually can be very dangerous with the amount of energy that they have. On the opposite end are radio waves, which have very low energy, not dangerous to us at all. So what we need to know about these, and we'll come back to this picture, is we need to talk about like what kind of waves and how these work. So all electromagnetic waves are what we call transverse waves. That means that the motion of the particles is perpendicular to the direction of the wave. So perpendicular, remember, is like this, that 90-degree angle or that right angle. So that means the particles go up and down, for example, as the wave goes side to side. So let me show you this little, let's see if it'll work, this little animation. So you can see the particles go up and down, but the wave itself goes from left to right. Okay, so let's go back to here. All right, so one other thing about electromagnetic waves is they do not require a medium, which means they don't need matter, they don't need air or a liquid or anything to travel. So these waves will go through space, whereas sound waves do need a medium. So if you yell in space, because there are no or so minimal particles, you will not hear anything. So the wave we're talking about looks like this. All right, just like if I said draw a wave, this is probably similar to what you draw. And some parts that we should note are the wavelength and the frequency. So the wavelength is from any one point in a wave to that same point in the next wave. And it's exactly what you think it is. It is the length of a wave. So in the description written here, it's distance between two consecutive peaks or troughs. So it could, like here I have peaks or crests from top to top. We could go like from here to here. That would be the same wavelength because the waves are all going to be uniform in size. So is a length, so they're measured in things like centimeters or meters, or if it's really tiny, we could get into millimeters or even nanometers or even smaller. If they're really big, we can start talking kilometers, like some radio waves are actually kilometers long. Frequency is the number of waves that pass through a given point per second. So it's how many waves go by you. So like if you were standing still and you were counting the waves, it'd be in 1 second, how many waves did you see? So frequency is measured in what we call hertz. So hertz is the unit that is equivalent to, you can see it written here, S minus 1. So hertz is abbreviated Hz, which is, like I said, S minus 1, which is simplified, or maybe it's more complex, as 1 over S. And you've probably seen this in math, where if you have 1 over x squared, that's the same as x to the negative exponent when you move it up to the numerator. So that's all this is. IB prefers to write it this S minus 1. They don't like to put numbers or symbols or units in the denominator. So they're always going to put them in the numerator like this. So what we should note is that wavelength and frequency are related in that as your wavelength increases, so think about that, as the waves get longer, so like this wave right here, you're going to see fewer waves per second compared to a wave that has a shorter wavelength. Okay, so if we call this like wave A and we call this wave B, wave A will have a longer wavelength and you'll see fewer waves per second, so a lower frequency. Whereas wave B has a shorter wavelength and you'd have a higher frequency. Because the waves are closer together, as you stand there and watch them go by, you're going to see more waves per second. So the thing to note here is that wavelength and frequency are inversely related. That means as one increases, the other decrease. Inverse would be opposite. So this brings us to the relationship in terms of an equation. Wavelength times a frequency will give you the speed, because wavelength is measured in meters, let's say, or centimeters, some length unit. And if we multiply that times our frequency unit, which is 1/seconds, we would get something like meters per second, which is a speed. How far do you go in a certain amount of time? So speed of a wave, we're going to talk about that. We're going to use the letter C, and I'll get to that Y in a second. Wavelength is this funny little symbol. It's the Greek letter lambda, so it looks like kind of like a little wave with a line coming down from it. And frequency is the Greek letter nu, and it's kind of like this little cursive V looking thing. So our equation is C for speed of light equals wavelength times frequency. And that speed that they all travel at is 3 × 10⁸ meters per second. This is the speed of light. Light is, as far as we know, the fastest thing. It will travel 300 million meters in 1 second, which is extremely fast. We have not been able to get anything exactly at the speed of light, but we have been very close, and we can talk about that more in class. So let's see if we can do a problem with this. So let's say a student is listening to the FM radio station B96 while doing their chemistry homework. This radio station has a frequency of 9.63 × 10⁷ hertz. That 96, that's in megahertz. So I just did the conversion already to hertz. So if radio waves travel at the speed of light, what is the wavelength of these waves? So what we have here in hertz, we have our frequency. So 9.63 × 10⁷ hertz. If it's traveling at the speed of light, our speed is 3.00 × 10⁸ meters per second. And the question is, what is the wavelength? So our equation is speed of light is wavelength times frequency. We're solving for wavelength, so I'm going to divide both sides by frequency, which gives me the fact that the wavelength will be the speed of light over the frequency. And now I'm ready to plug in my numbers. I always like to write my numbers one time. I don't do the algebra with the numbers in them because I don't want to write more and I don't want to make a mistake, because I'm much more likely to do that if I'm writing longer things more often. So I write 3.00 × 10⁸ meters per second. Notice I write the unit, and I'll show you why it matters. Divided by the frequency, 9.63 × 10⁷. And hertz, remember, is 1/seconds. And I'm going to write 1/seconds because hopefully you can see if you're dividing by seconds, you have seconds in the denominator of both your units, seconds will divide out. And the unit you're left with is meters, which is a unit for wavelength. So now I just need to type this in my calculator. So I'm going to type in 3 × 10⁸. Remember the calculator, you need to use your scientific notation button. So this part right here, remember, is that button. For a lot of you, it's 2 capital E's. That's the button you push. If you don't know which button, or you have never used that before, you can ask me, or you can Google it for your calculator. So I type in 3, my EE button, and then I type my exponent 8, divided by 9.63, my EE button, and then 7. When I type that in, I'm going to round this to 3 sig digs because both my values have 3. So my answer would be 3.11 meters. So it's just over 3 meters long is what one of these radio waves would have. And the higher your frequency, the higher that hertz number, the shorter your wavelengths are actually going to be, because you're seeing more waves per second, higher frequency. and that means they're actually going to have to be closer together.